Swayam Prabha. Digital India. Educated India.
Game of chess, okay? You're playing chess. How will you model this as an MVP? Should we model it as an MVP? So, first question again, is this episodic or continuing? So, in this case, I think the answer is quite clear, right? Games of chess end, okay? In fact, I think there are some rules built into the game that will guarantee probably that any game of chess will terminate after a finite number of steps, right? So, there's no point thinking of it as an infinite trajectory. And because it is episodic, right? It's going to terminate. You don't need to do any discounting. Okay, so this is actually the common practice with many board games. Usually, the outcome of the game is known only at the very end. Right? Did white win or did black win or was it a draw? So you can assign rewards of +1, 0, and -1. Right? If you're playing white, right, and based on whether you won, drew, or lost. Suppose you are playing white, and you can afford to give no rewards in between. Okay, so you go from one state to another, taking actions, give no rewards. Finally, right, where you reach, whether you lost or drew or won, that should decide the reward that you're given. And if that is -1, 0, and 1, then maximizing expected long-term reward will correspond to playing a game of chess that is successful. Okay, so well, it's not known whether chess has a winning strategy for white or not, right? So we can maybe just do the best we can, but at least in theory, right, there's no reason to give any rewards other than something at the very end. In practice, right, there are some reasons you might give intermediate rewards based on the material advantage, things like that. But at least conceptually, it's not needed. So I've told you about the reward function, but not really told you about states and actions here, right? So what are states, first of all, when you're playing chess? So if you're playing white, right, this is maybe your starting state. You'll make a move, but the configuration that results after you've made a move is not really a state from your point of view, right? It's a state in which black has to make a move. Okay, so white's next state, right, which becomes available is only after black has also made a move. Okay, so in some sense, black is part of the agent's environment rather than part of the agent itself. If white is the agent, then you should act as though black is a part of the environment. And herein comes in a very subtle point. Now, if there is a fixed strategy that black is playing, okay, so maybe there is a program that is controlling black that, depending on its state, will take an action, right? Then this is actually an MDP from white's point of view, okay, in the sense that when it takes an action, there's actually a fixed probability of getting a next state and a reward, right? It depends only on state. On the other hand, if black is itself, let's say, changing its behavior with time, okay, from the same state, maybe it can do different things at different points of time, then it's not strictly Markovian from white's point of view. Okay, so this is something that you need to be aware of. So usually games like chess, right, are modeled as two-player game, okay, as something that's a generalization of an MDP that has multiple agents. But if we assume that black is a fixed strategy, right, you can just fold it into the agent's environment and think of white's perspective of this whole thing as something that's like an MDP. Okay, totally different example, right? I mean, this is increasingly happening all around the world. There are wildfires that are bringing down forests, that are causing global warming, right? Can we do something about it with our knowledge of MDPs? Okay, it turns out we can, and here is the reference you should look at. So here is the way that controlling wildfires, right, preventing them, can be thought of as a sequential decision-making problem. Okay, so imagine that you have a forest now, and also imagine, let us say that the forest is divided into a number of cells. Okay, each cell having some amount of area and described by the kind of foliage, right, that grows on that cell. So the state of the forest, right, can be described by descriptors of each of these cells. Okay, is this part dry, right? How much timber has collected in this part? Is there a precipitation and water happening in this particular cell? etc. Okay, there's a geospatial sort of description of that area, that is state. Now, it is a well-known strategy that it is actually a good idea to prophylactically go and start small fires, controlled fires every once in a while in a forest. Okay, so that before the accumulation of timber really goes beyond a threshold and you have these uncontrolled fires, you can sort of nip it in the bud, so to say, right? So the actions that are meaningful interventions in a situation like this are you going and sending a team of people who will either start a small fire and finish up, or just clear out some area, right? Or have other interventions, maybe, right? Maybe they go and spray a chemical in some particular area that will affect the dynamics of the whole system in terms of the spread of fire and the chance of triggering fire, etc. The transitions happen according to the laws of nature. There are certain ways in which fire spreads. There's a certain probability with which lightning will strike some place. So maybe you can model some of these. And what is your reward function? So ideally, the biggest penalty you get is when there is uncontrolled fire, right? A lot of foliage, forest gets burned down. At the same time, you want to also minimize the number of interventions that you do. So this is usually a constraint. We usually don't have as many personnel or resources for going and intervening in the forest, right, as ideally we should. And so you want to minimize the number of interventions while at the same time minimizing the uncontrolled fires. Okay, so you will somehow fold in these two things into a single reward function. So if, for example, if you're saying R of S, A, S prime, right? If S prime is a state in which there's huge conflagration, then R of S, A, S prime must be a big negative number. If A, right, involved you going and doing a intervention, that should incur some penalty, right, etc. Okay, so again, look at the reference, you'll get an idea of how to formulate this as an MDP. And with these three examples, I hope I have convinced you that the number of problems around us that can be modeled as MDPs is immense, and the variety is also immense. Okay, so MDPs are a very generic formulation that really can describe fairly reasonably well, okay, various different control problems. Okay, so through the course we will probably cover some more examples that can be modeled and solved using MDPs. But feel free to look around. Okay, you can look, just search for applications of MDPs. You'll find lots and lots of them. Okay, all right. And I hope this has also convinced you that we are not doing purely an academic exercise. Many of the methods that we will cover in this class, right, can eventually be used to bridge all the way from theory to practice, right, and solve some of these very relevant problems in the world around us. Before we move on, I want to give you one final example of an MDP that's not really a real world application, but one that I suspect you will see has some resemblance to something you've seen before. So this is an MDP that has just a single state. Okay, that's S1. It's got K actions, and these are actions I have shown using different colors. Now, rather than take R of SA S prime as a fixed number, right, as we have done earlier, let's consider the variant where it's a random variable. Okay, so when you take A from state S and go to S prime, well, S and S prime both have to be state 1 over here. The reward that you will get will be drawn from the distribution corresponding to action A, right? So, for example, you will get something drawn uniformly from 2 to 4. Okay, if you pick the first action, you pick the second action, you will get something drawn from -1 to 3, etc. Okay. Now, if this is the MDP that we are interacting with, does this MDP have a different name? Right, something that you already know about? Turns out, yes, this MDP is also known as a multi-arm bandit. Okay, you can think of each of these actions as an arm that you're pulling. It doesn't really change state, right? It's sometimes called a stateless system or a system with just one state. You see that you're going to get random rewards, and therefore there will be some optimal arm, optimality being defined by which has the highest expected reward, right? Now, when we did bandits, right, the question that we were wrestling with is the fact that these rewards were random. Okay, the whole effort was to make sense of what is the reality that is hiding behind this randomness, right? And therefore, we had to explore. We also had to exploit in order to minimize regret, etc. With MDPs, right, what we are doing right now is assuming that these distributions are actually given to us, right, or at least the reward, expected reward is given to us. In some sense, that means you are given that the expected reward of this arm is 3, right, of this arm is 1, of this arm is half, etc. And therefore, the problem of computing an optimal policy is trivial, right? You have to look at the expected reward of each of these arms and just find an arm which gets the maximum, which has the maximum expected reward. There's no exploring, exploiting. You are given the expectations, right? So if this is actually a single state system, then it's quite trivial to compute the optimal action, which is also here the optimal policy. But when you do have multiple states, right, and you have transitions going from one state to another, it's no longer trivial to compute an optimal policy, right? So even if you are given the transition probabilities and rewards and you're doing planning, finding an optimal policy through computation is not obvious or easy, right? So that's what we're dealing with right now. Farther downstream, right, we will actually do both of these two things together. We will assume that we are not given the actual transition probabilities and rewards. Those are also things that we will end up having to sample, right, and still having to learn good policies from that sequential interaction, right? When we solve that, we are solving the reinforcement learning problem. Okay, that's literally where we are going, right? After doing bandits and MDP planning, the two of them come together in reinforcement learning. Okay, all right, good. So that situates, right, where we are with MDPs. There is a non-trivial computational problem to solve, even when the information about the transition probabilities and rewards is given. As our final module this week, let's look at what's called policy evaluation. This is a very useful tool, something that is going to be used in designing algorithms that can find pi star, okay, which solve the MDP planning problem. Okay, so in order to do this, let's take a closer look at our definition of state value. So now, right, and going forwards, let's go with our definition being infinite discounted reward. Right, this is what it was. V pi of S is the expected value of first time step reward plus gamma times second time step reward, etc. Okay, for ever, assuming you're following pi and starting from S. So why is there an expectation over here, right? Why is there the need for an expectation? Because the very next state that you will reach, right, by starting at S and taking action pi of S, that is random. Right, so first thing we do is let's just consider every possible next state that you can reach and divide this into a sum, okay, over n such next states. So the probability T of S, pi of S, S prime, you'll reach S prime, right? And you can look at the same expected long-term reward of R0, R1, gamma squared R2, conditioned not only on starting from S0 but also having reached S prime and taking a sum over all possible S prime. Okay, so nothing fancy over here. Just to make sure you're not confused, the fact that we're saying S and S prime does not mean these have to be different states, right? When you have a self loop, a transition to the same state, S0 and S1 could be the same state. Okay, so S prime is every state in S, and we are starting at state little s. Okay, so as a next step, let's split this up. So it looks like all that I'm doing here is taking this expectation, which is of a sum, as a sum of two expectations. First, only the R0 part, and then the R1 plus gamma, R2, etc. So notice that all of these second term onwards have a multiplying gamma, right? So we've taken the gamma out, and we have one less gamma to write inside. But again, that's an infinite sum. Now let's look at each of these terms individually. Okay, so I mean, look at the first term, right? What is the expected value of R0 if you started at S0 and you've reached S1? Okay, by definition, this is precisely what was R of S, pi of S, S prime, right? In fact, it's not even a random variable according to our convention. Even if it was, the expected value would be R of S pi of S prime, let's say. And as for the second term, right, this is where we are using a very important property, the fact that our data is coming from an MDP. Okay, so all I have done is this. I have said that the expected value of R1 plus gamma R2 plus etc. right, given S0 was S and S1 was S prime, is the same as the expectation of that sum just given S1 equal to S prime. Okay, so why are we able to get rid of the S0 equal to S? We are because we know that we are interacting with an MDP, right? The probability of going forward from S prime does not in any way depend on the fact that you came from S, right? So this is literally invoking the Markovian assumption. Okay, so now we keep the first term as it is, stare a little bit hard at the second term, the expectation over this policy. What does this look like? This is the expected value of R1 plus gamma times R2 plus etc. Given that at time 1 you were at S prime, right? So imagine just counting time from 1 rather than counting it from 0, right? Suppose you had a new variable t prime that started at 1, right? This would be something like R0 plus gamma times R1 given S0 equal to S prime, right? With that new variable. This is what we know to be as V pi of S prime. Okay, this is the definition with which we started. So in summary, right, what we have is that V pi of S is the same thing as sum over S prime T of S pi of S prime, that multiplying the one-step reward of going from S to S prime by taking this action, plus gamma times the subsequent reward that you will gather by following pi from S prime, which is nothing but V pi of S prime. Okay, so what we have done in the course of this is really gotten rid of these random variables, right, the expectation, and instead replaced it with quantities that we are given, right, from our MDP. We are given T, we are given R. Of course, what we are not given is the V's themselves, but these are what we have to try and calculate. Okay, so this equation, this LHS equal to RHS, remember that there is one such LHS for each state S. Suppose we fix pi, right? Then we literally have this same V pi of S being equal to this sum for every single state S on the left hand side, right? So this set of equations, okay, V pi of S, I mean, there's basically what you had on the previous slide, one for each state S, right? This set of equations is called Bellman's equations, okay? So Richard Bellman was the real pioneer of this whole area of work with MDPs, dynamic programming, back in the 50s. Okay, so presumably it's in his honor. And what do we notice about these equations? Right. First of all, don't forget that we have n states. Right. Let's say that these states were named S1 through Sn. So what we notice is there are n equations. Okay, so each state appears once on the left-hand side. So there are n equations. There are also n unknowns. What we don't know in these equations are these V pi of S values. Right? Sometimes they come on the LHS, sometimes they come on the RHS. But there are n of them. There are n states, right? So there are n such unknowns. On top of that, you can see that these equations are linear, right? So this is of the form y is equal to I don't know, mx plus c, or I don't know your favorite form of describing an equation, but the variables on the right, they get multiplied by a scalar, right, and then summed up, etc. That becomes the variable on the left. So the relationship is certainly linear. So if you have n linear equations and n unknowns, right, you know how to deal with it. One thing to, of course, make sure is the fact that it will have a solution, right? So if the discount factor gamma is less than 1, right, this set of equations is guaranteed to have a unique solution. Okay, it's not very hard to show, right? This is because if you think of this as AX equal to B, right, the A matrix has some special structure because of these transition probabilities. Transition probabilities are all between 0 and 1, and they sum up to 1, right? So because of that, you'll be able to show, right, as long as gamma is less than 1, there will be a unique solution. And therefore, right, what does this mean? It means if you're given a policy pi, evaluating it, okay, which means computing its value function, that can be done by solving a system of n linear equations in n unknowns. Okay, that's relatively easy to do. One more thing to mention, you can do basically the same thing even if you use gamma equal to 1, as long as the task is episodic. Okay, if the task is episodic, you're allowed to use no discounting, which means you set gamma equal to 1. You have to be a little bit careful. What you have to do is when you have a terminal state, right, you have to fix the value of the terminal state to be 0. I mean, that's the reasonable thing to do, right? Once you're in the terminal state, you don't go out, nothing happens. So just fix, right, give it a value of 0 and write Bellman's equations only using the other non-terminal states, okay? And as long as the task was actually episodic, you're guaranteed again to have a unique solution, okay? All right. This step of taking a policy and computing its value function in this way by solving Bellman's equations is called policy evaluation. Okay, computing v pi for any given policy pi, that's called policy evaluation. Okay, so it might sound a little bit surprising to you, but at this point, right, we've already done enough to answer a basic question related to MDP planning. Okay, so when I say are we done with this topic, I mean are we really done with MDP planning as a topic? And why am I saying that? For the following reason. Okay, early on in today's presentation, I gave you the result that among all policies for a given MDP, there will be at least one optimal policy pi star. Okay, you can take that for granted. What we have done just on the previous slide is to say that if you give me a fixed policy pi, you can calculate the value function of that policy pi by solving Bellman's equations, okay, which is relatively straightforward to do. Now think about this. Can you just put these two ideas together and come up with an algorithm that, given an arbitrary MDP, will compute an optimal policy for that MDP? Okay, these two are different things. Bellman's equations are useful for you. If you're given some arbitrary policy, you can find out what its value function is, right? But the original problem we were chasing is, given an MDP, find an optimal policy for that MDP. Can you already do it? You can, okay? You've done enough to be able to do that. You can do it in the following way, right? We know that there's a finite number of policies. Take each policy and compute its value function by solving Bellman's equations, okay? And we know that there is an optimal policy, which means one of those policies is going to be dominating, right, in terms of the value function, every other policy. So that you can find out by just doing comparisons, right? So although this might be a naive way of doing it, we do already have a proof of concept. We have a legitimate algorithm for finding pi star, right, for a given MDP. Of course, how naive is this? If we look at it in terms of complexity, the basic rate determining step is the number of policies, right? There are k to the n policies. So each of them you're going to evaluate, right? Solving Bellman's equations is, I mean, if you do it the standard way, it's something like an n cubed operation. Okay, you can do a little bit better, but it's basically polynomial in the number of states and actions multiplying the total number of policies. So although this is okay, right? It's correct and it's finite complexity. We hope to be able to do a little bit better. Okay, so the direction in which we will take this next week is to come up with algorithms which will also solve for pi star, but spend less time doing it. Okay, you can exploit the structure of the MDP and try and do better than this number of arithmetic operations over here. Okay, all right. So before concluding, okay, I'm going to give you one more definition. This is a definition that we're not going to use today. We're more or less at the end of this lecture, but we're going to find very useful as we carry things forward. Just like we defined the value function of policy pi, we can define something called the action value function of policy pi. Okay, this is called q pi rather than v pi. V pi had a single argument, right? Given a state, it would give you the value of that state. Q takes two arguments, a state and an action. Okay, and it is defined like this. Q pi of SA is the expected long-term reward you get by starting at state S taking action A at the very first time step, at t equal to 0, you act according to A, okay? But thereafter, right, once you reach your next state, you act according to pi, right, which means you take actions according to the policy pi. Okay, it's just very slightly different from always following the same policy. So right from the get-go, don't follow pi. Just the very first time step, you take this action A, okay, which is given to you as an input. Something is going to happen, you'll go somewhere. Thereafter, you act according to pi, okay? So in fact, even if you, let's say after one time step, find yourself in the same state, right, as your starting state, you'll take the action given by pi, okay? You will not take A if these are different actions. Okay, that's the definition of q pi of s comma A. And in English, right, I already told you this, it is the expected long-term reward from starting at s, taking A at time equal to 0, and for time greater than equal to 1, acting according to pi. Now, this function is called the action value function, okay? Q is called the action value function of pi. And if you do something similar to our working for obtaining Bellman's equations, you will see that q pi of SA can be written down as this sum, okay, of over S prime of T of SA S prime, because that's the action you're taking. The one-step reward, R of SA S prime plus gamma times V pi of S prime. There's a pi over here, because once you've reached S prime, you're acting according to pi, okay? Now, just for your satisfaction, you can note that if the action you are taking, if q pi is being evaluated for pi of s itself, right? If the action you're looking at is the same that pi will take, then q pi of s will be the same as v pi of s. You can sort of plug it in here and see that if you put pi of s over here, right, then what you have is v pi of s, right? Now, once you have v, right, q is not very difficult to obtain either. So you can just plug in v here, and then for each state action pair, you have to sort of multiply out transition probabilities, add rewards, etc. So in a further n squared k operations, you can get q. Okay. So when we say policy evaluation, you should sort of think that the product of policy evaluation is both v and q. Okay. So getting q from v is not such a big deal. Okay. It's just a further polynomial number of operations. So usually when we say policy evaluation, we mean getting v, but loosely sometimes you might say do policy evaluation and get q. Okay. So from this slide, it should be clear to you that that's relatively straightforward again for us to do. One other note, we said that every MDP will have an optimal policy, but it could have multiple optimal policies. We also said that all these optimal policies will have the same value function, V star. It's also the case that all optimal policies will have the same action value function, that is called Q star. Okay, there can be multiple optimal policies, but if you look at their action value functions, right, their Qs, those will all be the same, right? So every MDP has a unique value, optimal value function, as well as a unique optimal action value function. Okay, so I've not, of course, told you what we're going to do with Q, pi, and Q star. They're going to be useful for us when we design other algorithms next week. Okay, so just be familiar with what's going on here. We'll put it to use next week. Let me summarize what we've done this week. Okay, we've started a new, fresh, interesting topic, MDPs, Markov decision problems, which are an abstraction of sequential decision making. So in the early part of the lecture, we defined the relevant quantities, what an MDP is, what a policy is. A policy is a way of encoding behavior, and a value function is a way of saying how good is a policy. Okay, all those we defined mathematically and said the MDP planning problem is that of, given an MDP, find an optimal policy for that MDP. The problem is well defined because every MDP is guaranteed to have an optimal policy. Thereafter, we saw some other definitions of value functions, definitions of rewards, definitions of the actual task itself. I mean, not really a definition. The fact that a task can be both continuing and episodic, right, is something that we visited in section 3. I hope convinced you that there are many applications in the real world of MDPs. You can abstract real problems into MDPs, solve for them, and then take your controller and put it back in the real world, right? By doing that, You can fly helicopters, you can play good chess, you can put out forest fires, etc. Finally, right, we took the important step of policy evaluation. Okay, so policy evaluation is not already solving the MDP planning problem, but given a fixed policy, we saw that there is a relatively straightforward way of computing its value function. Okay, that happens by solving Bellman's equations, which are linear equations, n linear equations in n unknowns. We thereafter also used V pi to define Q pi, which we have not put to use, but that's coming up for you next week. Okay, good. So thank you. That's week 4 done. As usual, bring up questions if you have any, and I'll see you next week. Bye.